Makoeto wished to attend this conference, but at the last minute, the Department of Energy, U.S. Department of Energy, decided not to fund his trip. So he asked me to give the talk, which I hope I can do to your satisfaction. Tom has been making tritium for the last 7 years, using various gas discharge techniques between palladium and deuterium. And over that time, his technique and understanding has grown, the sophistication has increased, and his success has increased. And during that time also, his work has been subjected to extensive peer review at Los Alamos and survived. And I might mention that a peer review at Los Alamos is far more intense than any peer review from any journal. Unfortunately, the pathological skepticism that haunts this field has taken its toll, and it's very likely that Tom's work will terminate this year. Tom started by looking for tritium in various pure samples of palladium. These are listed here in the first column. The samples that show an asterisk are ones that gave excess tritium. And the first one, the good fellow B1, was the all-time favorite, giving between 1/10 and 2/10 nanocurious per hour of tritium, quite reproducibly. Unfortunately, they ran out of the stuff, and it's been somewhat of a problem repeating that. But it was recognized that certain impurities in the palladium wire very likely play a role. But there are so many impurities, and at such low levels, it's very difficult to sort it out. So Tom started having alloys made up of various kinds in a brute force attempt to discover what effect these alloys might have and find out which ones are the source of the tritium. And the alloys that he studied are listed here. Some of these have been looked at, some of them have not. A number of them listed with the asterisk have in fact given excess tritium, but not to the level of the pure material. Now the technique that he uses consists of a gas discharge cell, which is located here, that is subjected to a pulsed high voltage. I'll show the cell, the high voltage characteristics a little later. Then deuterium gas is pumped through a loop such that it eventually passes through a tritium detector. So he can see tritium in real time as it grows in. In addition to that, the gas can be sampled, oxidized, condensed as water, and that water then can be counted with a scintillation counter to be certain that in fact what he's measuring is tritium, and to give a redundant measurement. This shows the conditions in the cell, and you can see there's a pulse. This is an ideal pulse, I might add. There's a lot of ringing, and it's very messy, but this is the ideal way it looks. So he puts 1,500 to 2,500 volts on it, 2 to 4 amperes of power over a short period of time, 5 to 50 microseconds or milliseconds. And this causes a discharge, and it's during that discharge that the tritium is produced. He found recently, somewhat unexpectedly, that the discharge is not what loads the palladium. The palladium must load prior to the discharge by gas loading. And that's very sensitive to the nature of the palladium as well as the nature of the gas. And he's found now that many of the samples, perhaps, that were looked at in the past that did not work, probably did not work because they did not load. He now has a method to test the gas ability to load, and so he can do essentially like a canary in a mine, check the gas to make sure that it's suitable. by loading palladium, another piece of palladium that he can measure, where he can measure the resistance and see the loading characteristics. Once that problem was solved, things began to improve, but unfortunately he seems to have run out of time. The discharge looks like this. He's tried a number of variations. This is an arc discharge, didn't work very well at all. This was the first variation where there's a thin wire and a plate, and the discharge takes place between those two with gas pressure backing the plate. That did in fact produce tritium. They did away with that using a plate now without the gas behind it. That wasn't quite so successful. Now the present technique consists of a wire of palladium, a wire of palladium as the cathode, and then a discharge. And the crucial point is that the discharge conditions need to be such that it does not extend up to this insulator. That was the flaw in this case. Sure. Because as the discharge touches the insulator, it sputters off material which gets onto the palladium, which renders it useless. There are all these subtleties. I mean, not only do you have to fight the irreproducible nature of palladium, but then there are all these little subtleties within the apparatus that frequently are sort of either ignored or assumed they're not there, and all of us are subjected to that. And it's just a methodical, brute force sorting out of the variables that you actually get to the truth of the matter. And he has been systematically doing that. This shows the loading characteristics of a wire in the deuterium. It's not particularly interesting. Everybody knows how palladium loads. This shows a typical run. This is real data in real time. This is the pressure, and on this scale, this would be 1,000 millimeters right here. The 10 would be 1,000 millimeters. So he's at 1 atmosphere. He pumps it down to the pressure that one wants to have. This is the temperature of this is the temperature of the cell. It isn't truly the sample. You can't get that temperature, but you get the temperature of the cell itself. And this green line is the room temperature. So the discharge starts here, the temperature of the cell rises, and the pressure remains constant, but the tritium proceeds to rise. The tritium level, the best tritium level is about 100 times his sensitivity. Typically, he gets tritium levels that are 5 to 10 times the sensitivity. So it's well above the background, and you can see here that this is clearly resolvable from 0. This is another run. As is the case with all properties of palladium, you get variations. And here's such a variation. But you can see this is run with hydrogen. He's done that. It's absolutely dead on background. The small deviation there is certainly within the air, but the tritium-producing reactions are clearly resolvable and do all kinds of weird things depending upon what he does to it. Here's another example. Hydrogen gas, plasma's on, the tritium begins to rise. This is the tritium concentration nanocuries per liter. This is the Goodfellow wire that I was telling you was so good. You can see that it really is quite spectacular. There's no ambiguity about it at all. And the tritium then is oxidized out as water, subjected to assimilation counting, so you know absolutely that it's tritium. There's nothing, there's no room for skepticism, at least in these measurements. Here's an example of some of the alloys, and it's shown to show this particular effect. Just recently, this is very recent data, he ran this rhodium alloy, cobalt rhodium alloy, and got this very intriguing behavior. I mean, you can can see sudden big burst of tritium, and then a continual rise. Unfortunately, the wire broke at that point, and unfortunately, he's run out of time, so he can't really go back and repeat it. So, as is true of nature, nature's peculiarities, it sucks you in, and then it gives you a little taste of what you can see, and then you're out of the game. And so that's what's happened here. This is just enough to keep him interested for time necessary to reestablish his funding, hopefully. All of the samples have been examined for gamma emission. This is a typical gamma spectrum showing peaks which are background. There are no delayed gammas from his samples. He has looked for neutrons under certain conditions. The amount of tritium he's making is so small that even given the known tritium to neutron ratios from 10 to the minus 5, 10 to the minus 9, given that ratio, he would not be able to see neutrons at all. So he can set a limit, but there are essentially no neutrons associated with this. And he would hope to be able to make more tritium to be able to get a more precise measure of that ratio. But there is no gamma either. Okay, the conclusions. Summary of results. There's no tritium produced at low pressures. You have to be above a certain composition within the palladium for tritium to be produced. You get reduced tritium at high temperatures, and that's undoubtedly because at high temperatures the palladium is deloading. Hydrogen additions do not enhance the effect, so we're not looking at the alleged helium-3 production or some other kind of reaction involving both deuterium and hydrogen. Surface modifiers are important but not enabling. And those surface modifiers, of course, will affect a lot of different parameters, the most obvious of which is the loading ability of the material. You need to eliminate poison from the gas, and that's something he's keenly aware of right now. Reduced tritium output at palladium is anneal. Now, that's rather interesting. That's saying that the morphology of the palladium is exceedingly important, and you need to have palladium that is unannealed. Reduced tritium output of the palladium is stress relief, and so obviously it's the annealing that is causing stress relief, and so that's the relationship. Alloys can reduce tritium. It isn't clear at this point whether they do it better than pure palladium. Say, let's see, most tritium is found in the gas, with 30% in the palladium itself. And that makes sense. I mean, some of it would be dissolved. Extreme non-equilibrium, well, we won't get into that. That's too complicated to explain. No hot fusion is present under these conditions as measured by the absence of neutrons. No unidentified gamma seen after the test. And the plasma loading system is promising if the stoichiometry can be measured reliably, because that is one of the important variables. Okay, well, thank you very much.
Thanks, Ed. We still have time to pick up some questions. Please. Okay. Please. Dr. Morrison.
If I understand, the loading is based on 1 atmosphere of tritium. Now, I thought...
No, not 1 atmosphere of tritium, but deuterium. But it is even 1 atmosphere. He's actually running it at some partial pressure.
Yeah. Right. So, how much is this loading? Is it about 0.3 or something?
How much is what?
How much is the loading?
The loading is about 0.5 to 0.6.
So this result is in contradiction with what we had the previous 3 days, which said you must have 0.8, 0.9, 0.99.
It's clear that the conditions required for heat production and the conditions required for tritium production are somewhat different. That they're not, it's not the same nuclear reaction. It's apparently not even the same environment within the piece, and it is subject to different pressure effects.
See, that's a very big conclusion.
Well, it is a conclusion that is clearly derivable from the observation, if you believe the observation. I mean, that's the hope.
I understand it correctly, though, I mean, this is the loading not under discharge. When you discharge the plug, you really don't know. I mean, what is the loading at least in local or whatever. I believe that in order to get to this kind of effect, there must be some local loading which is quite higher than the beta phase loading.
That's a good point, and it's true that he only has an average, as we all do, for that matter. And the discharge is surely, well, since it's required, it is doing something, and that something that it's doing could very well be producing enhanced loading at the tip of that piece or someplace on it, which is a prerequisite for tritium production. So you can't say that. Yeah.
Finish?
Yes, please.
We have a lot of questions. Maybe Professor Frenchman?
I've just a very quick question. Those yields of tritium per liter, nanocuries per liter of gas. Was this per liter of gas at STP or was it per liter of gas at 200 chlor?
Okay, that's a question I'm not sure I can answer. You need Tom to give you that, but I would suspect if he has been as thorough as I expect he is, that it would be under standard conditions.
So, can you explain a little bit more about the effect of carbon dioxide? Because usually the carbon dioxide has the effect of enhancing cracking of materials. So, if this is the reason, looks something like a frat emission phenomena or a field.
The carbon dioxide has a number of effects, but the main reason for putting it in is to oxidize the hydrogen deuterium to form water and allow the tritium to be taken out and analyzed. It's another one of his techniques for getting water out of the system. But having said that, it does have an effect on the phenomenon itself, which is, at this point, I don't think truly understood. But yes, carbon dioxide under normal conditions does weird things. And of course, this is a weird effect. Who knows what happens?
We have pretty time to pick up at least 3 questions. Dr. Makoeto.
Yeah, I just want to talk a little bit to this issue of loading and have you respond. And this loading and this local loading, as Giuliano pointed out, that there's loading and activity. It's the chemical potential that's important. And you can achieve 0.6 loading at the temperature of this cathode, you have an extraordinary chemical activity. The threshold loading that we talk about, 0.9 or whatever, at ambient temperature, if you can achieve 0.6 at 300 degrees, you've achieved a far greater chemical activity.
Yes, that's a good point. Now, the discharge, at least Tom believes that the discharge did not heat up this wire excessively. But to the extent that it does, true enough, it's going to have that effect. And again, we don't know what the local values are. So we're really flying blind in this respect. All we can say, or all he can say, is that you must at least achieve a prerequisite loading to start with of some value, which is much lower than what we're used to.
We will pick more questions, please.
というのを in Russia, group in Ruchi, headed by Ramadan, made a similar experiment with molybdenum and other metals, and getting similar results, getting high concentration of tritium. And I'm very interested in such an experiment with discharge. So I want to have some comment from Dr. Ramadan.
Please,
I have one question. Your conclusion about temperature dependence for metals was made for palladium and all materials in your list.
Yeah, yes, the temperature of the palladium in there is unknown, but not very high. Tom feels that it's possibly not even as high as 100 degrees, but the precise values are not known.
We made opposite result on temperature. Very high thing. You have dependence tritium generation rate versus temperature. In coordinates logarithm tritium generation rate and abscissa versus temperature. Reverse. This dependence close to linear. Increased temperature on 200 degrees. Product was increased tritium generation rate on 1 order. Very strong dependence on tritium generation rate. Dependence tritium generation rate about mixture deuterium in protium have sharp peak for concentration about 10% deuterium in hydrogen. Exceed for this concentration about 1 order. Thank you.
Thank you. We have a lot of questions. We still have 5 minutes. Let me see. Dr. Tom Patel and Dr. Professor Zhang. Please, first, Tom Patel.
Does Tom have any suggestions as to the reactions producing the tritium? I noticed he tried some beryllium alloys, and I talked to him and he says, well, they were not so successful. But it is known that beryllium has a DT reaction, that's positive Q, and carbon-13 also, and oxygen 17. So those are the options that he has other than the DD reaction, and assuming that it isn't a DD reaction, it's been completely distorted away from its normal tritium to neutron ratio. So does he have any suggestions as to what that reaction might be?
Well, I don't think he has any suggestions that I could defend. He has explored many impurities such as beryllium. One of the complexities of this field is that although beryllium might be involved in the nuclear reaction, once it's in the palladium, it changes the chemistry of the palladium so that it may take the palladium alloy out of the regime that permits the reaction to occur at all. So it's a very complicated thing to figure out at this point. So I don't know that any conclusions can be drawn at this point.
Professor Zhang, only 2 minutes.
Today the decay section is right of heating.
It decays by beta. That's right. 12.3 year half-life.
Okay. The last word, please.
I would like to ask if there were different voltages tried in the glow discharge. I thought I saw 2,500 volts, but I wondered if there were others also. And if there were, was there some minimum voltage needed in order to make the tritium, in order to create the tritium?
Yes, he's tried a wide variety of voltages and a wide variety of geometries. The problem is to obtain a sustained discharge. And so that limits the voltage pressure regime in which you can operate. But he's explored a wide variety of pressures and voltages. It isn't, at this point, it isn't totally clear what those effects are because the palladium itself is sufficiently variable that it can mask many of these effects.
We still have questions, but we have to move on. Yeah, the last one, because he came on much earlier.
Yeah, did the measurement of loading get determined solely by the pressure drop in the cell? Or is there some other method that's being used to determine loading?
He has two methods available to him. The pressure drop is the easiest one to deal with, and the other is to take the piece out and deload it externally. Now, this is a 50 milligram piece of palladium, so there's not much deuterium in it. So it's, for a matter of any gun, yes. So, but those are the two techniques available. The gas pressure change is the easiest one to deal with.
How rapidly can he determine the pressure change so that he can look at the dynamics of the loading process?
Well, he can do that in real time, essentially fractions of a second resolution in his data acquisition system.
Thank you.
Thanks, Ed. It's a very nice talk.
Okay, next. Number 32. The title is Reaction Rates of the DD Reaction in Metal at Very Low Energies by Yuki, Sato, Otsuki, Yorita, Aoki, Yamazaki, and Kasagi of Tohoku University. The speaker is Professor Takagi, please.
Today, I'll talk about the recent subject on the reaction rates of the DD reaction in metal at very low energies. Since 1989, we have been investigating the low energy nuclear reactions in metal induced by neutron bombardment. Why? Because if I want to make a relation with a cold fusion with a nuclear reaction, there is a big question. Namely, we have to overcome the large Coulomb barrier. For example, if the DD reaction is really happening in the metal, so the height of the Coulomb barrier is something around 150 kV. It's let's see, it's something like 10 to the 6th times of the thermal energy of neutron. And also, as discussed from the beginning of this conference, I mean from the beginning of this cold fusion business started, there are a big difference between usual non-reaction of D plus D, because D plus D reaction goes to 50% goes to P plus T channel, and another 50% goes to N plus helium free channel. And even if we consider the alpha decay alpha channels, it's something like it's negligibly small. So therefore, from the nuclear physics point of view, we have to think about really the reaction rate in metal can be enhanced or not. This is one of the questions. So we decided to measure the reaction rate in metal as according to the traditional nuclear physics approach. And also, for the second point, we searched for the reactions other than D plus D channel. I mean, other than non-D plus D reactions. For that purpose, we bombarded the deuteron on the various metals with a neutron energy, in this case, something a little bit higher, something around the 100 keV region. So today, I want to show you the result of this low energy research in this 1 or 2 years. But before going to this subject, I just quickly show the recent result of this number 2 subject. Because last conference, we proposed yes, there is some kind of reactions occurring in metal. It's not a traditional D plus D reaction. There is the reaction which involves at least 3 deuterons. And first type, we are saying that it's a sequential reaction. Of course, it can be happen. And in this case, first, the reaction proceeded 2 steps. First step is a D plus D reaction, makes, for example, N plus helium-3, and the produced helium-3 can interact with another deuteron and makes alpha plus protons. And in addition to this reaction, we proposed something new type reaction. It's simultaneous 3-body deuteron reactions. If the deuteron interact simultaneously, then makes alpha, proton, and neutron. Why we propose this type? Because the energy spectra, what we observe actually in the deuteron bombardment of metals, we observe the very energetic protons. So this is the proton spectra, which I already shown in the last conference, and this is a proton spectra. You can see the energy scale of this. So up to, let's say, 17 MeV, we have seen the protons. And this kind of protons cannot be explained by the usual non-D plus D reaction, because you know the Q value of the D plus D goes to D plus T channel. It's only 4 MeV. So what we propose is there is a 2 kind of reaction here. One is just I told you, the 2-step sequential reactions, which was shown by these blue lines, and clearly the behavior of the spectrum shape are well explained by this 2-step sequential reaction process. And also we saw this continuous curve, and then our speculation is that this continuous path might come from D plus D simultaneous reaction. And if this kind of reaction can be happen, then we should see the alpha particle also. So we did measure the alpha particle and saw the similar spectra for the alpha particles. You see, this is the energy of the alpha particle. You couldn't get that alpha particle anyway if you consider the usual D plus D reaction, because as I told you, the branching ratio of the alpha particle, alpha production is only less than 10 to the minus 6. So what I showed you here is the expected curve from the sequential reaction process. In this case, the threshold is too high, so just we see as a continuous part, which I made the same calculation for this green line, and this is corresponding to the phase space for the three-body reactions. And of course, we saw that this kind of alpha particles for various metal. For example, this is the original one, titanium, deuterated titanium. And the zirconium target. Also, we see what I'm showing here is the two-dimensional spectra of the delta E versus E. So here the clear indication of alpha particle. And for gold, and for platinum, and so on. So right now, our conclusion right now for this second point, second subject is we have seen the alpha particles in bombarding the deuterons on various metals. So this is not only the titanium, but also the general future for any metal, I think. And of course, our speculation is just based on a single spectrum. So we have to make a real consensus measurement between proton and alpha particles. Then we will have real evidence for that reaction processes, which will be done maybe within next year, I guess. So I switched to the first subject. I told you one of the problems to do the nuclear reaction with a very low bombarding energies is the large Coulomb barrier. So I just show the figure. This is a potential versus distance between two charged particles. Of course, our nuclear experiment is done by using the target of gas type or the solid type. But anyway, there should be the electron. So if the electron cloud is here, the bare Coulomb barrier is reduced by the electron shielding. So at least we could see this effect if we do the experiment. And usually the low energy fusion cross sections is expressed by this formula, which consists of SE, so-called astrophysical S factor, and a famous gamma factor. So which tells us the height of Coulomb barrier. And what we want to know is that the Coulomb barrier is the same as the bare nuclei, or the different from it when we did the nuclear reaction in metal. And for the reaction, GD reaction with the gas target, the one of the group of Germany measured the reaction cross-section for the DPT reaction. And what they plotted here, I showed here, is the so-called S factor, astrophysical S factor versus center of mass incident energy, center of mass energy of incident particle. And usually the S factor can be parameterized at high energy region where the Coulomb, electron shielding effect cannot be seen. So, but what they saw is the increase of S factor at the very low incident energy region. And then they deduced the screening potential, something around 25 electron volt for a gas target case. In the metal case, of course, there is no accurate measurement, but what we expected is something like this potential. This is the effective potential for D plus D in titanium calculated by Ichimaru some years ago. And here the bare DD potential, just a Coulomb potential. And for atom case, of course, the electron shield effect we can see here. Then something lower in this region. And in metal, according to Ichimaru's calculation, we have a reduction of the Coulomb potential. And he was estimated. I calculated the effective screening potential, which is about something around 50 electron volt for titanium case. So we constructed the small machine to do the very low energy nuclear reaction by the help of this basic research project of new hydrogen energy project. So here our machine, we have a dioplasmaton ion source. The D plus or D2 plus beam is getting from this ion source, and we extracted the voltage something around 25 kilovolt because we want to get a high current beam. And the beam is just a little bit bended to separate the atomic beam and molecular beams. And then here we have a deceleration or acceleration electrode. So if we operate this one as the acceleration mode, then we can go up to the 100 keV. And if we change the polarity of the applied electric field, then we can get the neutron beam down to, let's say, 1 keV or so. So, but inside the chamber, we put the filter magnet just to separate from the neutral beam, because if the ion extracted from the ion source, and in this case, the energy is something around 20 keV, and during this transported stage, the ion can be neutralized. That means they cannot affect the deceleration voltage and electric field. So they still have a very large, high energy. So we put the neutral beam filter magnet here. So the real low energy beam is bent by this magnet and hit a target here. And we put the signal detectors here. If we measure this, just a simple, using just one single counter, we can have this kind of spectrum. This is the proton from this channel, and this is triton from this channel, and this is helium-3 from this channel. So in this case, the measurement time is very short. That's why we couldn't, fortunately, we don't have so many electric noises. But if we lower the energy, let's say, down to 4 MeV, oh, sorry, 4 keV, then we need the time to accumulate the events. Therefore, sometimes electron noise destroy our spectra. But anyway, we did some single measurement, and we got this ratio. The reaction rate for the D plus D goes to P plus T, and the D plus D versus D plus D goes to N plus K3. So in this case, I just average the incident energy. I will explain later. But anyway, there is a gas target measurement by Graff et al., green point, and almost 1.0 down to this place. And here the yellow points are the data which I took, let's see, maybe 2 or 3 years ago. And these two coincide very well. And here the red points are our new data. So if I draw some line, there might be something here, but which I don't know. Maybe the chairman, Dr. Lee, might be happy to look at this some deep structure here. And then we should take delta E measurement if we want to go down more. So we put the 2 silicon surface barrier detectors, one is a transmission type, which has thickness of 50 micrometer, and behind it is another thin 100 micrometer silicon detector. By using this delta E technique, we can have a very nice spectrum without any electric noise. So this is the time spectrum between the delta E and E detector. Here you can see the coincidence peak here. So these are due to the random coincidence means one of them might be electric noise. And here I plotted again 2-dimensional spectra, delta E versus E. And in this case, without any selection, you see the noises around here. But if you put the gate on the top TDC spectrum, the noise are all gone, and only the proton signal or the real, I would say, real signal can remain. And this is the spectrum projected on the E plus delta E. So only one peak can be recognized, and no background at all, because we selected the time correlation between delta and E. Therefore, we could go down. I don't know, maybe if we do the measurement for 1 month, then we might go down 1.5 keV or so. But anyway, up to now, we have data down to 2.55 keV. So here the result for the in titanium case. And as you see, the reaction rate decreases very quickly. Only the, let's see, 1, 2, 3 keV difference makes 1, 2, 3, 4 order of magnitude difference. And then this is the prediction without the streaming to predict how to predict these reaction rate. We did a fixed target measurement. Therefore, the incident neutron slowing down when the neutron is in titanium. So therefore, we have to we have to know that this energy when the reaction occurs, and also we have to know the density of neutron here, and we have to know the reaction cross section, and then the reaction rate. I mean the yield, target yield, is predicted according to this formula, and also we have to know the let's say stopping power. So for these, I just assume the ND is a uniform distribution, and sigma cross section is from a parameterization of Bosch and Hay. In this parameterization, we cannot expect a spring effect because these are parameterized at rather high energies. And also for the stopping power, we took the Anderson-Ziegler's value. So the experimental data shown was divided by this predicted value, and we plot like this. So if the upper part is just a raw data, we call it the enhancement because we could expect the enhancement for the electronic screening. But actually the statistics not so good, so the data is fluctuated. In order to get the more good statistics, we just averaged these each 3 point and get the lower figure. Here, we clearly see the enhancement of reaction rate below 4 kV, although the enhancement is not so great. I mean, just only something around 10% enhancement. And of course, in order to check the validity of our, this enhancement is really has meaning or not, we just proceed the chi-square test for the data which I just shown. And the chi-square tells us that our screening potential is something like 19 plus minus 12 electron volt with this energy region. We changed the host metal from titanium to the other metals, and we tried one for the yttrium case here. The same treatment has been done for this measurement and also for the analysis, and this is again the predicted value without screening, and the same data and the same technique was done. And if you look at this carefully, even in this graph, you can see the enhancement at below 5 kV. And this enhancement...
Sorry, 5 minutes.
Okay. If I put I plot the same way as I did for the titanium case. For the yttrium case, the real enhancement occurs below 5 kV, and also the amount of enhancement is higher than the titanium case, something like 30%. And this red line corresponding to the screening potential of 60 electron volt. And also, I want to show this chi-square test, result of the chi-square test. It clearly shows the minimum value is something like 60 electron volt. Okay. The screening potential, the question is that the screening potential derived by this way is a constant, even if we change the incident energy. There is some calculation, but not in the metal case. This is a calculation for the atom, target is atom, and one of my colleagues, theoretical colleague, Hideo and Takigawa calculated using, I don't know the real method, but anyway, dynamical norm method. So according to their calculations, this screening energy can be changed by changing the incident energy. So the value which we took in this energy region is not the constant, I would say. So I'll summarize my talk. We proceed the E plus D reaction in metal at the incident energy lower than 5 keV. And we saw the reaction rates are really enhanced in metal. And this enhancement can be interpreted as the electron screening. And if we did such kind of analysis, we deduced the electron screening potential is something around 20 MeV for titanium metal and 60 electron volt. 60 electron volt in yttrium case. But it should be noticed here, in atom case, the screening potential is something like 20 electron volt. This is the experimental result for the atom case. And also, this screening potential, of course, cannot explain the cold fusion, because if a cold fusion rate we require, for example, this rate, then we need 100 electron volt screening potential. And also, if we require this order, we need this kind of screening potential. But also, I think it's important point. The enhancement strongly depends on metal. I mean, that depends on the environment of the nuclear reaction itself. So our result tells us that if we use the titanium, just 10% of enhancement, but we change the metal, the enhancement is changed. And so that's why we should study the mechanism of this enhancement for the very low energy nuclear reactions. And we will try many methods, and also we can think we could change the conditions and so on. Okay, thank you very much.
Thank you. Time has come, so just show one question.
Thank you. I think this is one of the most important experiments that has been presented at this meeting. And what it shows, if you do a good, careful experiment, you get good, reasonable results. And you should compare this with the previous experiment, because you knew exactly your beam energy. When you have a glow discharge, a spark discharge, one doesn't know what the energy instant particles are in. And in glow discharge, you can sometimes get accumulation, you get little local points, and you get very high energies at times, which exactly as you have shown, will produce reaction, will produce tritium inside the metal. It's entirely normal. And another nice thing you showed was you have secondary interactions, where you showed that alpha particle is produced. May I suggest you look for 14 MeV neutrons, which should also be produced as a secondary interaction in the DT reaction.
Well, you're saying that the alpha particle is from...
A secondary interaction. I mean, you produce helium-3 about 800 keV, and 800 keV is enough energy that will interact with another deuteron and give you your secondary interaction.
I suspected that the alpha particle is from the secondary reaction.
Yes.
And we tried many experiments. For example, I just put the target, let's see. Yeah, I consider the neutron case. And I didn't explain the detail, but the negative result. So I'm quite, and also for the impurity case. And I tried almost I can do it.
Yes. No, I think it's very nice evidence. It's similar to the work that was done in Brookhaven, which was greatly discussed and was a false result and caused great arguments. The other thing, as you have shown, is that the ratio of neutron to tritium is very close to 1.
Yes, that's right.
And I mean, there's nothing abnormal. It's not 10 to the minus 5 or 10 to the minus 8. 1.
That's true.
It's and the third thing you show is that inside metals, the reactions are basically normal. There's 10, 20, 30% differences. There's no anomalies happening in metals.
Right.
There's only the electron screening. And the other thing where I think your results are very important is the determination of the astrophysical S factors, which are terribly important when you consider like the nuclear reactions of the sun. And I think these low energies is very good work. Congratulations.
I'm sorry. We can continue to discuss in lunchtime. Thank you very much, Professor Saito.
Next speaker is Professor Kim.
Michael. By the way, Doug is leaving not because he doesn't like my theory, but he has to catch a club. He apologized. I don't know how many of you've seen this cartoon, and it was relevant to us many years. But after this conference, situation may be changing. If Celani is really producing gold, maybe everyone will start getting funding, including me. I will follow this outline. And some of the topic I will discuss is published in this journal. Last one, Physical Review C, is coming out very soon. Let me look at the first how conventional gamma effect was derived. We have two potential programs for, let's say, DD or nuclear reaction. And this is standard way to describe two potential quantum scattering theory in terms of S matrices and phase shapes. Now, semi-classical approach has been used in the past. That's the conventional approach. And you take this formula, but you substitute this thing with transmission coefficient. And the way transmission coefficient is obtained is to do WKB approximation and get a simple integral, and eventually you end up with famous gamma. And let me remind you, this result is not fully quantum mechanical. It's a semi-classical formula. And as you know, if you believe that gamma factor will be all out of business. But I insist that's classical, semi-classical formula, not the quantum formula. And I wanted to derive reaction rate in full quantum mechanical context. And the way we did was to use optical theorem. This is not conventional optical theorem. All the quantity here is angle integrated. Conventional optical theorem involves forward scattering amplitude, and that is a lot of problem if you have a Coulomb interaction, because Coulomb interaction is a singularity in forward direction. So we avoid this conventional optical theorem here. Instead, we develop another type, which is as rigorous as this one is. So by using this approach, this is quantum mechanical vibration now. We can identify cross-section, reaction cross-section we're looking at as imaginary part of elastic scattering country. That can be theoretically written in this form for two potential forms, where T satisfies this reference string equation. But of course, unless you know all the potential, strong potential, you can't really get this thing. We know roughly what it is, but still model dependent. So what we decided to do is look this problem in more general context. We parameterize this with a very simple two parameter, strength and some form factor. And for the two-channel case where elastic and only one open channel fusion is involved, and if it's S state at low energy, we can show, we have proven in one of the references that it has this form, that is separable form. So we take this form, and let's assume the Yukawa type with some range. Delta will be, inverse delta will be range of the interaction. Then you get this new formula. Now we change this form to this form, and more complicated form, yet we end up with this common factor. So we are very comfortable that this is indeed the feature of quantum mechanical derivation. So let's look at that term and what it can do for us to stay in the business. This has this structure, and if you make the interaction range inverse of beta large or beta small, it can be exactly same form but opposite sign to the gamma factor. Now you do not expect perfect translation because then you are talking about repulsive or attractive Coulomb force. But if somehow beta is very small, then you can accomplish near cancellation of gamma factor. Now, this is not ordinary potential in the real sense. It's the imaginary part of elastic scattering potential, effective potential. And if one can allow beta to be very small or large range, then of course you can hit the Franklin-Pons level, Jones level, whatever, with, let's say, electron screening, Thomas Perlman type combined. Now notice that to do that, we have to have a very long range interaction. So now the question is, does the nature allow us to have such a long range force? Now there are no long range force. Remember, this is long range force in the imaginary part of elastic scattering potential. One of the well-known potential is so-called electric polarization potential, which arises when two charged particles collide, they polarize the electrically and create a new type of effective interaction. And that has a 1/4 long range structure instead of very sharp Yukawa cutoff. But this doesn't help us because this is a real part of the elastic potential. Another long range force which nowadays becoming very popular is the so-called two neutron core type Halo. If two neutron is very weakly bound to the rest of the nuclei, then you can solve three-body program and find that there are long-range potential, which is again real, and it doesn't help for the fusion processes. There's one imaginary part, imaginary potential known. This comes from quote-unquote excitation, Coulomb excitation, and if you derive effective potential, you can get the attractive 1/r². And actually, this was encouragement to look for this possible scenario. Now, there are many planned experiments to explore halo state. This is a typical 2-neutron halo. Has an extraordinarily large size compared to non-halo nuclei. Now, halo state can be excited state, not necessarily ground state. And it's expected to appear along the neutron drift line, around here. And we don't know whether some of those nuclei might have loosely bound state. Those to be explored by future experiment. But there are known halo state or halo nuclei, ground state, excited state, and so on. So what this shows is that it could be excited state. So we took this experimental fact, and hopefully nature is kind enough to provide such excited state. For instance, for this case, if this product had the halo excited state, we show in this latest paper that there is a gamma factor translation, near translation gamma factor. Now, because time is short, I'm not going to give a derivation of that, but let me show what type of long-range interaction it generates and implication of it. This is a form we derive. It's excited P-wave state. But this may have an important consequence because not all of the nuclei, especially light nuclei, like the deuterium, helium-3, neutron, obviously don't have halo nuclear state. And this effect, enhancement effect, will not occur. If final nuclei had the halo state, excited state, then enhancement can occur, which means you can rule out lots of lighter elements and the gamma rays and neutrons. But the medium and the heavier nuclei, which might have halo excited state, will get the enormous enhancement of the cross-section, which may explain some of the transmutation results, but by no means completely. Now, there is a complete different mechanism, which I like to discuss. It's so-called continuum electron shielding. And the reason I got involved with this problem was in solar neutrino problem. This problem has not been solved exactly. They make approximation. No one has solved the three-body problem involving two positive, one negative charge. We are doing it, and it's complicated calculation numerically. So we wanted to look at the approximate solutions. And amazing thing happened. After you write the Schrödinger equation and make this original Schrödinger equation, and you can make approximation assuming this term by dimensional augment, this term is one of the other two, then you end up with this simplified approximate solution at the bottom. And if the condition is right, then you can have a gamma factor translation. And that condition is that the relative velocity between electron and proton is much smaller, or smaller than proton-proton relative velocity. That translates this kind of condition. If this condition is satisfied, you can write the equation solution this form, and then separate previous equation
those two forms. And if you want to know what is the behavior wave function between two protons, then you cancel those two terms and get this equation. So the gamma factor cancellation can be achieved. Now this may be related to idea of swimming electron layer proposed by Hora and Miley, but may provide a more basic justification of that model, because we are getting this result from three-body Schroedinger equation. If you look at the condition for various different cases, DD case, you have to satisfy this condition. These are kinetic energies. And if you pick a nucleus, you have this kind of condition. And in the metal, because conduction electrons have their Fermi distribution, and maybe if deuterium is mobile, which has Maxwell distribution, there are certain phase spaces where that condition may be satisfied. In particular, if you have a high density electron cluster, that condition will be satisfied too. I will come to that next bureau, but there is an observation by Ken Schroeder claiming that you can create a 1 micron size electron which contains Avogadro number cubic centimeter. So that's a 10 to 11 electron. And the lifetime is this order. And it may contain nuclei or ion to this order. And it can move this distance because velocity is almost 0.1 velocity of light, or because they apply electric field or potential to create this by discharge experiment is 2.7 kilowatt. Now, if this is confirmed by independent experiment, it has enormous implication for us. Incidentally, that problem was looked at these two plasma physicists to see whether one can obtain solution mimicking that electron cluster by solving Maxwell equation for plasma and recasting in form of Klein-Jordan equation. And this is the solution for amplitude problem. Here, the square of amplitude looks like Ken Schroeder's electron clusters. So what this means, if it's true, there are theoretical justifications, but we need to confirm experimentally by independent test. If it contains, let's say 10 to the 5 nuclei, the charge to mass ratio is still enormous because you have 1 million times more electrons. The proton mass is only 2,000 times heavier, so still charge to mass ratio is enormous, so that you can accelerate proton to this kinetic energy. Deuterium to this is 9.4 energy. If it's oxygen in the water or heavy water, you can accelerate to 56 energy. For this case, we're talking about hot fusion. Now, he has claimed that this electron cluster can be created at a low voltage, as low as 50 volt, in which case this kinetic energy will be order of 50 volts. So we still need continuum electrons shooting. And this is ideal because if those ions are moving together with the electrons, relative velocity between electron and the nuclei embedded is nearly zero, while they are moving faster to the target or going other places. So you might think of cluster impact nuclear fusion with this type of scenario. It could be as large as that, or it could be much weaker, which may happen in the metal. And once this type of reaction occurs, it's as if, for this case, it's as if you have an effectively negative charge, so that all kinds of nuclear reactions can occur. Direct reaction as well as or others. Those are to be studied in the future. How am I doing in time-wise?
7 minutes for total.
Huh?
You have 3 minutes.
How come you give me a 5 minutes warning?
5 minutes for discussion.
Okay. Actually, this is very interesting program, cluster impact fusion. And I'll show some of the picture Dash and other people had. If you send this thing with a lot of electron and hit the metal, you can create a shock wave and create a hotspot. So that can help too. It's becoming hot fusion. And another concept which might apply in this case is so-called magnetically insulated confinement, which originally proposed by Tasegawa and observed from laser fusion. What it is that the electrons sort of make this kind of current around it and create a magnetic field this way, so that the positive ions stay inside and focus and creating high density plasma. Now let's look at the Ken Schroeder's pictures. Instead of this paper we published in this journal, this was a Texas A&M meeting last month. And what he does is he has an anode and the electron gun about 1/6 centimeter apart, and then he applies about 3 kilovolt discharge potential megafarms. And this is some of the impact it makes, presumably this electron impact. And most interesting is he took Dash's
5 minutes.
Yes, paradigm electrode, and when he looked at the flat part, he did this kind. And later he bombarded Dash's sample with his electron cluster. And this is what he planned to get. I think this is so interesting that it ought to be confirmed by independent measurement by several groups. And remember famous picture of Miguel Dash, that at certain location like here, you don't see any impurity or new element. But if you pick this spot here, like here, he sees lots of new element. Presumably, most of this is not the original impurity. So let me conclude. There are at least 2 known mechanisms to me which can cancel gamma factor. First one is having excited heteronuclear state in the final nuclei. And that is a very important implication because not all of the nuclei in the final state might have that. Especially light element is not known to have that kind of state. So this mechanism favors creating medium or heavier elements. And of course, and another idea is the continuum electron shielding. And this may provide Gamma factor cancellation if it's in electron clusters. Fractal emission in metal might induce such a clusters. And of course, once this is achieved, your exit channel has all possibilities because it's as if a neutral particle is doing nuclear reaction. So we have to study those possibilities. And most interesting, intriguing part is that if indeed cluster impact nuclear fusion can be achieved by electron clusters, this may compete with laser fusion because it's once it's confirmed, it's easy to control. And it offers the possibility of a neutronic reactions as well. So let me stop here. I have a lot of stuff, but I'll stop here.
Thank you. Professor Freshman?
I think I lost the thread halfway through your presentation. The lithium-11, which is a fascinating species, this is a stable halo nucleus. Now, you are, let me get this straight. You
Which part? Halo nucleus.
The halo, lithium-11 is a very fascinating species.
Not necessarily stable.
What is the radius of the neutron orbit around? 10 Fermi?
Depends. If binding energy is nearly zero, it's really.
It's about half a G. It's a very low binding energy.
Right.
It's a half.
It depends upon binding energy. It's a proportional, inversely proportional to binding energy.
It's about half a MeV.
No. Some of them observe the 10 keV, 20 keV, which correspond to 5 to 10 Fermi.
Yeah. Now you are proposing the creation of an excited halo state. Now, if this is due to the targets, the species coming in on the target,
right,
you must also then create a low-lying state. You create a high-lying state and a low-lying state.
No, the mechanism is different. The final state, regardless of what you do in the entrance channel, it has its own spectrum, including this state.
Mm-hmm.
But there are another particle involved. So full three-body, the wave function in the final state is necessarily solution of three-body state. Mm-hmm. And you cannot just say ground state and let's say proton. Mm-hmm. It has to involve all the spectrum.
Well, I was just wondering whether there would be some funny processes in the low-lying states.
Low-lying state, if it's a binding energy large, it won't do it. It has to be very top near the continuum with a very small binding energy, like a 10 keV less. Yes?
I would like to first comment that it is very important that you have now the nuclear reactions, the proton reactions, within the swimming electron layer.
Yeah.
Of course, you see, we had only the general result in 88 of the swimming electron layer, and later the combination with good surfaces or interfaces for the business here was another story. But the detailed calculation now with your Australian equation is a great progress. And in this sense, I would like to mention, especially to the former talk, when the KEV deuterons are being stopped, they have a different screening in these few angstroms at the surface, and it's a bulk. And this has to be separated, and it's very important from your result to distinguish this.
Yes.
But elaborate a little bit, I would be...
This electron screen is different from Kasagi. He's talking about atomic electron screen. This is a continuum electron, which may or may not occur in the metal. It may occur.
One question. You said that I know the hollow state make a very strong effect for the reaction cross-section, but there is any candidate, for example, we have deuteron D2 electrolysis or something, because helium-3 and tritium should have some kind of level, and even if you consider that case, the reaction channel is just a P plus D and N plus helium-3.
Yeah, those nuclei do not have a halo state. We know helium-3 spectrum. Helium-4 mainly because there are many states up there. If you go more and more heavier nuclei, you get the very complex spectrum. In palladium, there are hundreds of states near continuum. And if one of that happens to be halo state, then this mechanism works. So it's a matter of identifying the state. Yes?
First off, I think you made a lot of progress.
Thank you very much.
No, it's true. I especially think, the identification of the halo state and sort of. I was curious if you could comment on the potential mechanisms for trapping energy. I mean, in other words, would you expect to see X-rays? Would you expect to see high energy particles? Would you expect to see?
This is a nuclear physics mechanism. Only solid state effect is continuum electron.
Right. So it would be in leaving the lattice. You would.
Right. My purpose is to address gamma vector cancellation in the entrance channel.
Right.
What happened afterward is your decision.
The interesting question, though, that's a follow-on to that kind of notion is the consideration of size. When you start getting down into particular dimensions, you might see damage. For example, I'm thinking in particular of Miley's kinds of structures. If you had high energy particles actually coming out, you might see.
This electron cluster may address that type of. If electron cluster can happen so often and equilibrium as you do in electrolysis, in cavities and cracks and so on, then it looks like a collective phenomena, and it might address your concern. But I don't know.
Professor Brisani.
Short comment about when in your list of the halo state. You know that there is a rather recent discovery of the pionic halo states that may have some relationship with that. Was it clear? And again, there is coming out this pionic state from there is a pocket of potential at long range coming out from again
I'm not saying this is the only possibility. This possibility we derive rigorously. It's a physical review C publication. There may be other possibility which we haven't investigated. So field is open. Only thing you need is a long-range imaginary part of elastic scattering.
It's exactly what I wanted to say. There is more and more evidences of the external states from other reactions.
Okay.
Thanks. Sorry, we cannot go further.
You should let me my question. One question.
Okay.
He came back for this, so we have to.
Yes, you're right.
For a second back for you. Just a simple question. Do you think it would be possible to check your theory by comparing it with the results of the previous talk from Duke University?
Duke University.
Can you check your theory by comparing with the results
for
of the previous
DD
experiment?
DD deuterium doesn't have any halo state, so no sense testing. You have to have a halo state. It is. Collaboration between behavior, deuterium in palladium, and occurrence of nuclear reaction observed by spontaneous measurement of excess heat and the nuclear product by Iwamura, Ito, Goto, and Toyota of Mitsubishi Heavy Industries. The speaker is Dr. Yama, please.
Thank you, Chairman. I'd like to talk about correlation between behavior of deuterium and palladium and occurrence of nuclear reactions observed by simultaneous measurement of excess heat and nuclear products. Contents of my presentation is as follows. First, I will mention about our new type of experimental system with intent to induce continuous nuclear reactions. Next, I will describe our experimental results on D by PD and X-ray emission and excess heat using the developed system. We previously reported that diffusion process of deuterium, in addition to high D by PD ratio, is an important factor for causing nuclear reactions by the method of gas release experiment in vacuum. Based on these experimental results, we developed a new apparatus. The basic idea of our apparatus is that we might control nuclear reactions in D2PD system by making continuous flow of deuterium and a high D by PD condition. This figure shows the cross-sectional view of our experimental system. It consists of two parts, an electrochemical cell for calorimetry and a vacuum chamber for nuclear measurement. Deuterium atoms are loaded by electrochemical potential into upper side of the palladium sample and released out from the lower side. Therefore, there exists continuous flow of deuterium atoms through the palladium. Excess heat is estimated by flow calorimetry. As for nuclear measurement, 3 X-ray detectors are equipped and 1 neutron detector. The first NAI detector is surrounded by lead block to reduce the background X-rays. The second and the third X-ray detector are located outside of the cell, looking at the surface of the palladium. And we have measured the pressure of the upper side of the electrolyte side and pressure of the vacuum chamber in order to estimate the absorption and desorption of deuterium through palladium. These are the photographs of the apparatus. The electrochemical cell is made by Teflon, as shown here, and this is the vacuum chamber. And we can see 2 NI detectors and 1 chemistry detector. And this photograph shows the measuring system. All the systems are located in the clean room where temperature and humidity are always kept constant. And they are electrically isolated from the outside of the clean room by using the stabilized power source. Here is a process chart of sample preparation. At first, we wash a palladium sample with acetone. And after that, we anneal the sample at 9 degrees centigrade for 10 hours under high vacuum conditions. And wash the sample with aqua regia. After that, some samples are ion spattered by MgO or aluminum, and some samples are electroplated by copper or platinum, and the others have no films. The size of the palladium is 25 millimeter by 25 millimeter, and the thickness is 1 millimeter. Let us move on to the next point. DYPD analysis is as follows. For electrolyte side, only one basic equation is applied, and we can calculate by this equation, and we can calculate the number of deuterons into the palladium by equation 2. As for vacuum side, equation of state and the mass balance equation are necessary. Combining equations 3 and 4, we obtain the equation number 6. Then D by PD ratio is estimated by equation 7, like this. Here is an example of DYPD analysis. In this case, the palladium sample has no film on it. In this view graph, blue line means the number of deuterons absorbed into the palladium, and the red line means the number of deuterons released out from the palladium, and the green line means the D/PD ratio. As we can see, D/PD ratio reaches about 0.8 even for the palladium sample without surface modification on the vacuum side. This figure shows the variation of absorption and desorption of deuterium. In these cases, procedures of preparation, sample preparation, are all the same. Horizontal lines mean the time, and the pink line, the pressure of electrolyte side, which is correspond to the quantity of deuterium into palladium. And the green line means the pressure of vacuum side. It corresponds to the derivative of quantity of deuterium released out for palladium. It is easy to see that conditions of absorption and desorption are greatly changed even for the palladium sample prepared by the same procedure. It shows that absorption and desorption behavior of deuterium is greatly influenced by the unknown factors. For example, impurity or surface condition of palladium. Let's move on to the next point. This figure shows the example of X-ray emission and its energy spectrum. This sample has aluminum thin film on it, and this data was obtained by X-ray detector in the vacuum chamber. Upper figure indicates time evolution of X-ray. X-ray count rate reaches over 10 times larger than that of background, as you see. And around this period, X-ray emission lasts for about 1 day. Energy spectrum of the X-ray emission is shown in the lower figure. X-ray energy distributes continuously like this. However, at present, we cannot explain consistently why such an energy spectrum was obtained. In addition, only one case we observed this type of X-ray emission. And so then we would like to try to reproduce the similar result. Next example shows simultaneous detection by upper side X-ray counters. In this figure, copper is electroplated on the palladium sample. Horizontal axis mean time, and orange line mean the X-ray 1 in the vacuum chamber, and red line and blue lines are X-ray 2 and 3 respectively. They are located upper side of the palladium as shown in this small figure. We can see a coincidence of X-ray 2 and 3 is very good. On the other hand, the count of X-ray 1 are almost equal to the count of background. Judging from these experimental results, sudden nuclear reaction must occur on the electrolyte side of the palladium. For the thickness of palladium is 1 millimeter, reduction rate of X-ray through the palladium is larger than that through the D2O and the wall of the cell. This figure shows correlation between X-ray and the pressure change. Horizontal axis mean time, and red and blue line mean the X-ray 2 and 3. And X-ray 1 data is omitted because there is no significant increase of X-ray X-ray count in this case. Orange and red lines indicate the solution temperature, and green line indicates pressure in the vacuum chamber. In this case, we change the flow rate like this. We change the flow rate of coolant like this. If we change the flow rate of coolant, then temperature of palladium is changed, and migration of deuterium is affected. Therefore, pressure in vacuum chamber can be changed. Based on these experimental results, it seems that X-ray emission is related with the migration of deuterium in palladium. Next topic is on excess heat. This figure illustrates the excess heat analysis. Different point is that we should consider the removed D2 gas, the enthalpy removed by D2 gas through the top molecular pump. However, the enthalpy removed by D2 gas is negligible. And therefore, we evaluate by this ordinary equation 8. And the dissipated power is estimated by PD82O system. Here is the view graph on correlation between excess heat and the other parameters. Horizontal axis mean time, and the red line mean the excess heat, and the orange line current, and blue the X-ray count, and green pressure in vacuum chamber. At low current, 1.5 ampere, we could not see any excess heat. After making up the current up to 3 ampere, which corresponds to the 1.5 ampere per square centimeter, excess heat generation was observed. We investigate correlation between excess heat and nuclear products. However, Under our experimental condition, it is not clear between excess heat and nuclear products. These histograms show the comparison of the heat distribution between excess heat and no excess heat. In both cases, input current is 3 ampere, and total input power is about 40 watt. The difference of these cases is the sample treatment. EV39 has a thin film on MgO on the vacuum side of palladium, and EV40 has a thin film of Fe ion on the electrolyte side of palladium. It can be seen that mean value and the deviation of excess heat is larger than the, it can be seen that mean value and deviation of excess heat of EV39 is larger than those of EV40. Next, I would like to discuss on the experimental results we have obtained so far. The first point is on X-ray emission. We have experienced 14 times out of 40 that only upper side X-ray detectors show the significant increase of the X-ray counts, though X-ray detector in vacuum chamber did not. On the contrary, only one case X-ray was considered to be emitted from the vacuum side of palladium. This one is
Please come to the conclusion.
Okay. And first example, and therefore probability of X-ray emission on the electrolyte side of PD is higher than on the vacuum side, and I suppose that the reason is related to the local D by PD ratio. Since the local D by PD ratio is considered to be higher on the electrolyte side than that on vacuum side. Second point is the rate of event. If we assume a few mega electron-volt energy released by one event, value of excess heat we obtain correspond to the value from 10 to 10 to 10 to 12 events per sec. X-ray emission calculated by American radioisotope ranges from 10 to 2 to 10 to 4 events per sec. So excess heat and X-rays might be generated by different nuclear reactions. Perhaps I suppose I should not exclude the possibility that various nuclear release reactions occur and produce various nuclear ashes. Now I conclude my presentation. We developed a new type of experimental apparatus for simultaneous measurement of excess heat and nuclear products. Absorption and desorption behavior of deuterium in palladium is greatly influenced by the unknown factors. Correlation between excess heat and nuclear product is not clear under our experimental condition. X-ray emission seems to be related with the behavior of deuterium in palladium. We might suggest that various nuclear reactions occur in PDD2 system. Much work remains to be done in order to clarify the nature of cold fusion phenomena. Thank you.
Any short question or comment?
The X-ray spectrum you showed on EV8, is that typical? Could you put the view graph up again?
Not typical case. You mean the?
The X-ray
You
spectrum.
mean the?
Yes, that one, yes.
Only one case.
Only one case.
We obtained. So I cannot reproduce this result. Of course, I tried, but I could not.
What was the duration of that experiment? How long did that experiment take?
1 week. For 1 week.
Thank you very much.
Last question. Yes, please.
What is the solid angle in which you see yourself by X-ray detector?
I cannot answer exactly, but about 45 degrees of
Not a solid angle.
Sorry,
efficiency.
No, the solid angle.
Efficiency.
Or
How much of full pi you have?
Okay. The efficiency about 4%.
4%.
Yeah.
And what is the distance of the X-ray detector from the kit?
About 45 centimeters.
45.
Okay, thank you very much, Dr. Yoma.
Our next speaker is Tom Pastel. Search for the nuclear reaction product in heat producing palladium.
Thank you, Mr. Chairman. This is search for reaction products in heat-producing palladium, and otherwise known as cathode archaeology. Looking back at old cathodes that produced heat in various experiments to see if there was any difference in them relative to those materials that were out of which the cathode was made. So this particular, the approach that I've taken is to collect cathodes that produce excess heat in as large a quantity as I can find, collect virgin material from the same batch of metal, measure the stable isotope ratios in both by the same method, preferably non-destructively, and any changes may be related to the nuclear reaction that produced the heat, assuming that the reaction is not D plus D to make helium. If so, I couldn't possibly see any changes. But the fact that we don't see neutrons and tritium to any degree with heat led me to think that some other reaction might be the actual heat producer. Now, I've crudely shown the cathode that I chose as a C2 cathode from the SRI work. And if the cathodes were 3 in number, interleaved with 4 anodes, about a square inch of material, a sort of a multiple plate condenser sort of geometry. And I took a square centimeter of the cathode, which I hope, of course, is representative, and placed it in a thermal neutron beam to measure the neutrons that are captured by all the stable isotopes that actually capture neutrons in that sample. Now, we irradiated for 10 hours in the beam, collecting the prompt neutron capture gamma rays with a high-resolution germanium detector. And we do the same then with another 10-hour run with the virgin material. And finally, with neither, with just the Teflon bag that we had the samples in, did it for the background. And then when we get the counts, we have a whole series of, everybody has seen, I guess, a gamma ray peak. So I'll just show from some NIST work what a palladium gamma ray looks like for palladium 105. And this is the one I'm choosing because it's so clean relative to all other gamma rays in the system. And unfortunately, boron has a not quite so beautiful peak because the Doppler shifted. Because the captured gamma ray, captured in boron 10, results in alpha plus lithium 7, and it has a long enough lifetime to be shifted by about 20 kilovolts. Furthermore, the palladium has a few gamma rays that overlay this in such a way as to, so if you had pure boron, just with a little sodium impurity, this is what it would look like. It would be a very flat, 20 kilovolt wide, so-called peak. And this is, of course, a sodium peak, which is not in my samples I know